Hi everyone. This is our last video on proportion hypothesis tests, and thought I would again do an example from a real world problem, and that is water quality. We've already done quite a bit with water quality, and when we looked at hypothesis tests, or excuse me, confidence intervals, again this problem is drawn from Montana, the Gallatin River, the Spanish Creek, which flows into the Gallatin River, is a potential source of pollution. What is essentially causing the problem, a potential problem, is a bison breeding operation, which is on the Flying D Ranch. The Flying D Ranch again, let me go to bring up my pen. There you go. Oops, hold on. Okay, the Flying D Ranch flows through or contains the Spanish Creek. There's bison up in here. Does the bison, the byproducts, the waste from the bison, flow into Spanish Creek, which flows into the Gallatin? That's the question. Okay. Again, one way to monitor water quality is to look at macroinvertebrates or bugs. And again, what we're looking for is healthy species. Actually, healthy is pollution sensitive. They're indicative of healthy environment. So what we have is we've done this with a confidence interval. What I want to do with a hypothesis test now is we collect a sample of bugs, macroinvertebrates downstream, and there we are doing so. And what you can do then is you classify those. This is where it's qualitative data. So if you're on a test, sitting on a test, you know it's proportion because the data are qualitative. The macroinvertebrates are either healthy indicators, so pollution sensitive, or unhealthy indicators. So we took a random sample of 168 macroinvertebrates. 62 of those were healthy indicators. Now here's where the question differs from what we did in the previous videos. Based upon those data, can you conclude that the proportion of healthy indicators downstream of the Spanish Creek is less than the upstream proportion, which was 0.4? Okay, so that's a question. Either the proportion is or is not less than 0.4. Use alpha equals 0.05 is again sort of a clue that this is a hypothesis test. The way you start off any hypothesis test is you start off with defining your parameter of interest. And remember, the parameter is some aspect of the population. Okay, the parameter is, in this case, is P, the proportion of healthy indicators among all insects downstream of the Spanish Creek. The hypotheses, the null hypothesis, remember before upstream in the supposedly clean portion of the river, the proportion of healthy indicators is 0.4. So the null hypothesis is that P is equal to 0.4. This is always an equal statement. The alternative is given by, the clues to that are given by the question of interest. Is the proportion downstream less than the proportion upstream? So that's our alternative, that P is less than 0.4. The decision rule, which I'd like you to provide for me, reject H naught if the p-value is less than 0.05. This is called, by the way, the p-value approach. There's another approach called critical value. It leads to the same conclusion. It's just a sort of a slightly different way to go about this. But we're using the p-value approach. The test statistic is a proportion on your formula sheet. It would say proportion test. This is the formula that you'd be using to determine, basically identify and complete this test. All right, for this problem, we have the following data. We know that P naught, and P naught is what we think the proportion is under the null hypothesis. P naught is 0.4. P hat is the sample proportion. There were 168 bugs, randomly selected macroinvertebrates. 62 of those were healthy indicators. So that's 0.369. That's our sample proportion. The sample size N is 168. Using these values, plugging these into the test statistic, we get, and this is where I would encourage you to sort of follow along with your calculator, p hat minus p naught over what's called the standard error of your p hats, 0.4 times 1 minus 0.4 over 168. From the formula sheet, that gives us negative 0.8189. If you're using a normal table to find the probability, which we'll do, then round that to 2 decimal places, negative 0.82. Here's a graph. I'm really a visual learner. Here's a graph of the situation. If the null hypothesis is true, if the proportion of healthy indicators downstream is 0.4, we should see proportions close to 0.4. We took a sample. We got a sample proportion, p hat, of 0.369. That p hat has a z-score of negative 0.82, which means that 0.369 is a little less than 1 standard deviation less than this mean. The p-value is the probability of finding that p hat. How likely is that sample proportion if the null hypothesis is true? With a z-score of negative 0.82, you can hear my dog in the background too, by the way. He's barking at must be an invader walking across our sidewalk. And so you have to ignore him. Is you find, remember our normal table only gives you positive z-scores. So 0.82, this is to the hundredths, and that gives us a p-value, not a p-value, but a probability of 0.2939. Remember, our table always gives you what's between the mean and the score, 0.2939. There, you heard him loud and clear. My 12-pound guard dog. So let's go back to the graph. This is where the graph's really helpful. 0.2939 is this portion right here, but that's not what we're looking for. We're looking for the essentially evidence that we're getting less than 0.4. Again, remember the alternative was that p is less than 0.4. So that says you're going to be shading. You're looking for the probability from your sample proportion downward. It's consistent with this. If this is less than, you shade down the number line. So 0.2939, we're looking for the red portion. That's 0.5 minus 0.2939 for this normal curve. That gives us a p-value of 0.2061. Intuitively, what that says is that if the true proportion of downstream bugs is healthy macroinvertebrates is 0.4, the chance of seeing a sample proportion of about 0.369, about a 20% chance. So let's go to the last problem for this. Okay, the conclusion. And the conclusion would be, since the p-value, which is 0.2061, is greater than 0.05, do not reject H0. So there is no evidence, based upon these data at least, that the proportion of healthy indicators downstream of the Spanish Creek is less than 0.4. So in other words, there's no evidence that the Gallatin River is more polluted downstream of the Spanish Creek than it is upstream. Lastly, we want to check the validity anytime you conduct a hypothesis test. And notice that there's a slight difference between validity for a proportion hypothesis test and a proportion interval. We're given that there's a random sample of 168 insects. Remember, talk about it in the context of the problem. This is where the validity procedure differs slightly from the confidence interval. N times P naught. Remember, P naught is what we think P is under the null hypothesis. Our null hypothesis was that P equals 0.4, so P naught is 0.4. So 168 times 0.4 is 67.2. That's bigger than 10. N times 1 minus, that should be a P naught. equals 168 times 1 minus 0.4, 100.8, which is also bigger than 10. So the three validity conditions were met. That means the hypothesis test procedure is valid.